Okay, so in the past video, we basically looked at how to find the volume of solid revolution using the disk method. Today, we're going to do something similar, but we're going to call it the washer method. When we're looking at a specific region that we're trying to rotate around the x-axis or y-axis, before we had just one big region, right? One solid region. But we've seen before, like in section 6.1, when we're finding areas, sometimes instead of having the region be one region under one function, sometimes it's going to be the region between two different functions. And in that case is what happens. Well, if we're taking a region that is bounded between two functions, that really tells us that when we're trying to rotate, you're rotating this one solid region. So when you see it up here, and you get kind of a mirror image of it, you see this one solid piece, what happens? We end up getting some space in the middle that's kind of empty. And so in that case, when you're trying to find the volume, finding the volume is not just going to be a matter of finding the volume of the entire shape, but rather finding the volume of the solid part minus the entire shape, that is, minus the part that we don't want, minus the empty part. So kind of think about when we did before, when we were looking at areas, right? If you have trying to find an area of a shaded region, what did we do? We would say, okay, well, we don't really know what the area of the shaded region is directly because the shaded region is a really weird shape. But if we find the area of the square, subtract from it the area of a circle, we'll get the area of the leftover, which is the shaded region that we want. That's kind of the same idea here. So what we're going to do here is we're going to say, we want the area of the shaded region, or the volume, excuse me, of the shaded region. But how can we find the volume of the shaded region? The way we're going to find it is we're going to say, what is the volume of the entire shape? The whole thing. And then from there, subtract from it the volume of the inner part, which is this inner shape right here. By doing that, we get precisely what we're looking for, which is the volume of the outer part only. Okay. Now, because of the fact that when we cut something and we have, we cut perpendicular to the axis of rotation, we end up getting this circular shape. But in this case here, because of the fact that the shape has a hollow inside, so it looks something like this. If you've seen these in physics or other things, we use them in real life, we call these washers, right? So because of that, we're going to call this the washer method. So the washer method is basically saying, instead of finding the area of the entire region, we're going to find the area of the outer region. So we're going to find the area of this big circle over here. What's the area of the big circle? The area of the big circle is going to be pi times the radius square, where r represents the big radius, capital R. And then we subtract from it the area of the smaller circle. That's the part we don't want. Well, how do we figure out the area of the smaller circle? Well, that's just going to be pi times little radius square. If we take the area of the outside minus the area of the inside, we get exactly the area of the middle, and that's the part that we want. Both of these radiuses are going to, again, depend on the functions, right? So one of them is going to be the outer function, one of them is going to be the inner function, kind of like before what we did. We said which one is the top, which one is the bottom. So we're going to do the same idea here. Let's look at our image. So here we're going to take the function y equals square root of x. And then we're going to take the function y equals 1 over 10 times x. And notice how in this case here, we're going to bound it by x equals 4. So that's the region we're creating. Notice how in this case here, it's not a full solid, right? There's an empty space in the middle. So when we rotate this, it's going to create a shape that's circular when we cut, but there is going to be an empty space in the middle. So trying to find the area of the cross section, it's going to be the same thing as finding the area of a washer. And how are we going to find that area? We're going to find the area of the outside times the outside minus the area of the inside. Okay, so let's look at an example. We are going to go ahead and for all of these moving forward, when you're trying to find the area of a solid revolution using either the disk or washer method, we have to ask ourselves, is the region that we're rotating, is it fully solid or is there a space in between the region and the axis of revolution? If the space is completely filled in, then we just do the disk method. You're going to do pi r squared dx. If there is a space between the region and the axis of revolution, so here is my axis of revolution in this case, and there's a space between the region that we're rotating and the axis of revolution. In that case, we have to do a washer method, meaning that there is an empty space in the middle. So in that case, we have to find two radiuses. That's the only difference. We're going to do the outer radius squared minus the inner radius squared delta x, and then the rest of it becomes normal. Be careful when you're doing these. It's not the radius minus the radius squared. It's not that. It's that you have to take the radii and square them first and then subtract. Where does this come from? This comes from the fact that we're taking pi times the larger radius squared minus pi times the inner radius squared integrated, right? From a to b. Well, since they both have a pi, what can we do? We can factor a pi out of both of them and say take pi out and leave the rest, which is going to be radius squared minus radius squared dx or dy. So that's where this formula is coming from, okay? We're taking the area and we're just factoring the pi out. Notice how in this case here, if you do have a solid disk, then in that case, because there is no inner radius, it just means the inner radius is 0. So you're really saying it goes back to the same formula as pi r squared dx. All right, let's take an example. When we're trying to find the volume that is bounded by y equals x squared, y equals x, and it's rotated about the x-axis. Step number 1, we need to graph the region. So far, we've been given the bounds for these functions or for these regions, but there are going to be times where they don't give you the bounds. So if they don't give you the bounds, what that means is that the bounds are naturally created by the functions. By that, I mean that there's going to be somewhere where these two functions intersect, and that's going to be our bound for the region. So what we need to do is we need to figure out where do these two functions intersect. You can do this in two ways. You can either graph, or you can go ahead and say, where does x squared equal to x? Make the two functions equal to each other. If you do this, you'll see how you have move x to the other side, factor an x out, and you get that either x equals to 0 or x equals to 1, which means these two functions are meeting at x equals 0 and x equals 1. Let's go ahead and graph them. So the first one is going to be x squared, so 0 goes to 0, 1 goes to 1, 2 goes to 4. It'll look like this. The second one is going to look like y equals x. Let me be a little more accurate here. This is going to look like this. The parabola usually is a little bit steeper, and then y equals x is going to look like x, 0 goes to 0, 1 goes to 1, 2 goes to 2. So it looks something like this. This is y equals x. Notice how, because from the graph, I can also tell where they're meeting. They're meeting at 0 and they're meeting at 1. And the region that we're looking for in that case is going to be the region that's this one here. All right, now what are we going to do? We need to go ahead and bound this. We're going to have to rotate this region by the x-axis, which means this region is going to be rotated this way. So you should see a mirror image of the region down here. And we have this circular shape. And we see here that we have an empty space in the middle, don't we? So because of the fact that there is a space between the axis of revolution and the shape, that tells us that we're dealing with a washer method. All right, so that's step number one. Step number two, since we're dealing with a washer method, that means we have to take the integral from a to b of the big radius squared, the outer radius, minus the inner radius squared, dx or dy. All right, so I always start with, am I dealing with a dx or dy? Well, because we're rotating around a horizontal axis, we're dealing with a dx. Okay, if that's the case, my second part is, what are the bounds for the x? I'm dealing with a dx, which means I'm checking bounds for dx. So I'm going to go from the left side. What's the outer bound for this region? Well, this region is starting over here, which means starting at 0. And the region is ending over here, so it's ending at 1, which means my bounds are 0 and 1. The last part is figuring out the radii. The outer radius and the inner radius represent when you cut perpendicularly over here, draw a circle from the middle, from the axis of rotation, and the circle goes all the way out to the outer part of the region, which means that my radius is going to be from the middle, which is the axis of rotation, to the outermost function. Well, in this case, the outermost function was the line, which means my outer radius is x. All right, your second circle needs to go from the axis of rotation to the inner part, the part that you don't want, the empty space. Well, for this case here, the axis of rotation is going to be, the radius is going to go from the axis of rotation to the inside function, meaning the bottom function, which was in this case, y equals x squared. So my inner radius is x squared. And now that I have both of them, I can go ahead and plug it in to my formula and say the volume equals to the integral pi times the integral from 0 to 1 of the outer radius squared minus the inner radius squared dx. As you guys are doing this, make sure that you always simplify first before you do the integral, okay? So before integrating, I'm going to go ahead and simplify and say this is pi integral from 0 to 1 of x squared minus x to the 4th dx, which gives me pi x to the 3rd over 3 minus x to the 5 over 5 from 0 to 1, and then we plug them in. Plugging in the 1 gives me 1/3 minus 1/5. Plugging in the 0 will just give me 0 and 0 in both cases. So I am really taking 1/3 over minus 1/5. I'm going to go ahead and get the common denominator, multiply here by 5 and 5, multiply here by 3 and 3. So I get 5 over 15 minus 3 over 15, which gives me 2 over 15. So pi, 2 pi over 15, that is my volume. All right, let's try another one. For this last problem, let's try taking the same region and now rotate it around the y-axis. I'm going to start by the same exact thing. Remember, we have 3 steps here. Step number 1, we need to draw our function. Since we already have it drawn before, I'm just going to copy it. We know these guys met at 1 and 0. I had my x squared was in the bottom, my x was on top. So y equals x y equals x squared. These are the exact same results we had from the last section, from the last example. Now, the only difference is rather than rotating it this way, we are going to rotate around the y-axis. Okay. Rotating it this way, I get something that looks like this. The way you can tell if you're using the disk method or the washer method, look at your region and look at the axis of revolution. If there's a space, an empty space between your region, so here's my region in black, and the axis of revolution right here, because there's an empty space, that means we're using the washer method, meaning that we have to figure out the outer radius minus the inner radius. Okay, so number 2, because I know I'm using the washer method, I write down the formula for the washer method, which is going to be pi times outer radius squared minus inner radius squared dx or dy. So my first step, figure out, am I dealing with the dx or am I dealing with the dy? Second step, figure out the bounds. And then last step, we're going to figure out the radii, inner, outer, and inner. Okay, because we're rotating on the horizontal, vertical axis, meaning the y here, it's going to be x equals 0, or the y-axis. Anytime you're dealing around a vertical axis, you're going to be dealing with a dy. So our axis of rotation is a vertical line, and so our variable for the integral is going to be a y. So we're dealing with dy. This is important for the next step, because the next step says, okay, if you're dealing with the y, then in that case, the bounds have to be the bounds for y. So now we're not looking at left to right anymore. We're looking at what's the bottom of this region and what's the top of the region. Well, the region is bounded in the bottom by 0, and it's bounded on top. They met at 1 by 1. So it's going to be from 0 to 1. The last step is going to be finding our axis of, finding our radiuses. So the radius or radii, the first one is going to be the outer radius. So you just want to imagine like you took a circle around the entire outer part. So the radius is going to be from the middle to the outer side. Well, from the middle from the axis of rotation right here to the outer part, you're going from 0 back to who? Back to the y equals x squared. So this is going to be our function y equals x squared is our outer radius. But we have to be careful. Since we're plugging in a y, we can't put in x squared, right? Because you can't have an x and a y in the same integral. So what do we need to do? We need to convert this and say, instead of writing it as y equals x squared, we can write it down as x equals square root of y. So that is going to be our new radius. So instead of this, you write down square root of y. Same thing for the second one. The second one, we're going to have a circle, but instead of being from the axis of revolution to the outer part, we're going to do from the inner part. So now we're just looking at a circle that's inside. So this inside circle here, that's representing only the empty part, the radius is from the axis of revolution to the inner function. What's the inner function in this case? Well, in this case, the inner function is actually x. It's y equals x. But remember, we don't write down x. Instead, we write down x equals y. So y is our inner radius. Now we have all the pieces. The rest is just a matter of plugging it into our integral and doing the integral like usual. So it's going to be the inner radius is, the outer radius is square root of y squared. The inner radius is y. All of it is with respect to y. I simplify, gives me 0 to 1 of y minus y squared from dy. And integrating that will give me y squared over 2, y cubed over 3 from 0 to 1. Now, pi, plugging that in, I'll get 1/3, 1/2 minus 1/3. And then the second part is just going to give me 0 and 0. let's get the common denominator, multiply top by 3, bottom by 3, and here 2 and 2. So that'll give me pi times 3, 6 minus 2, 6, which gives you pi over 6. Notice how here my answer is actually different from the last one. The last one we had, I believe, 2 over 15, 2 pi over 15. Here we get pi over 6. That shows us that depending on what you're rotating around, your volume, even though it's the same exact region, the first one we rotate around the x-axis, so it would look like this. The second one you rotate around the y-axis. But because we're rotating around different axis of rotation, our volume actually ended up being completely different. So your answer isn't going to be the same just because you're dealing with the same starting region. The volume depends on the axis of rotation and the region that you're rotating.